go. All right. So this is the lab that you're going to see today. It is not released yet, so you won't be able to see it just yet. So I'm going to read this out so that you guys understand, what this is and how to get started with this kind of more like a project. It is not exactly a lab because I don't think you can get it done within, um, the lab time. All right. So the first thing is you need to have an environment to write C programs. So when I say C, it is C++, okay, because C is really a subset of C++. So once you have learned how to program in C++, C is like, okay, it's actually a subset of that. It is a easier and simpler language compared to C++. So let me ask you, in your CISP360, what environment did you use to write your programs? Go ahead. Code blocks. Replit, okay. Sorry? Dev C. Okay, all right. Yep.
Linux, GCC.
Linux GCC. Okay, well that I'm familiar with that one. Command line stuff. All right. So regardless of which environment you use, you just have to have access to one. So for people who do not have access to a C programming environment anymore, for whatever reason, okay, because some people might have taken CISP360 and use a Linux server environment to gain access to GCC. I mean, you can install GCC in Windows, but it's not like super easy. It's super duper easy in Linux, but in Windows it's not as easy. So for those people, you have a choice. You can go to online GDB. This is a link to online GDB, which is like exactly like Replit. So I'll show you what online GDB looks like. This is online GDB. It is entirely just a website. You can sign in. So let me go ahead and sign in as myself. So just log in, and you can log in using your Google, Facebook, or GitHub. So I'm going to sign in using Google. All right, so once you sign in, you can actually save your file. This is free, okay? You don't have to pay anything. You can use a free Google account to do this. So if you're concerned about this website collecting your personal data and whatnot, just sign up for a free new Google account and use it with online GDB. I have never had a problem with online GDB, just so that you know. So what it is a programming environment, okay? And I'll show you some of the features later on, related to the homework assignment. Is that okay so far? With Replit, does it have a debugger? Because I know one of you said you use Replit for C and C++. Does it come with a debugger? Can you pause the program execution and examine variables and whatnot? Because last time I tried it, which is a few years ago, pre-pandemic, it did not have that feature. Um, so does anyone know? Yep.
I think I saw it all the time. I never used it.
Say again?
In the debugger,
Uh-huh.
I saw it an option, but I didn't really use it.
Okay, you did not use it. Okay. I can look into it, but online GDB does come with a debugger, and it is actually the same as GDB. So for anyone who knows how to use GDB, this is like super easy. Yep, go ahead.
It seems like there is a debugger actually.
Oh, okay. All right, great. So if you want to use Replit, that's fine too. Okay, because I just want to make sure whatever environment you use, you have access to a debugger. Okay. So let me go ahead and go back to the project. So the project is right here. So the project gives you a source file to begin with. This is a single source file, which means you can use it on online GDB, because online GDB cannot take on multiple source files. So I have to kind of put everything into one single source file. So let me download it first. Okay, so download is right click and then save link as. And I like my browser to ask me where to save it to. Okay, I think I need to click it first. Then choose download from here. It's a canvas thing. Alrighty. Nope. There we go. So I'm going to download this as monolith-1 .c, and I'm putting it into my temp folder. Obviously, when you download it, you can put it anywhere you want, as long as you remember where you put it. All right, so there is that, and close. All right, so now if I switch back to online GDB, I can now paste that file into online GDB. I can replace this entire code here because I'm giving you the beginning point or the starting point of the entire project. All right, so here is time for a little bit of a command line sorcery. In this case, it is xclib cell clip redirect from the file that I just downloaded to, which is monolith-1.c. And this allows me to paste it, over here. So Control V, and now we have the entire program pasted here. The program, the portion that is given to you is 164 lines long-ish, okay, because the last line is just an empty line. I provide you with a lot of stuff already, so there's no need to do your parsing. Remember the regular expression stuff, backslash equal to, backslash plus, and all that stuff. That's already done for you, okay? If you're curious about how that is done, you're more than welcome to read my source code and comment and whatnot, okay? But you're not required to. So the way this program works is you have to run it and pass an argument to it. So it processes what we call the argc, which is argument count, and argv, which is the actual argument itself. It's an array of strings. So when you run the command from the command line interface, you can supply additional arguments to the command, and those are all captured by argc, which is reporting a count, how many things are included on the command line command, and also argv, which is an array of strings where each string is one part of the command line component. So that part is done for you already. It only recognizes one option, which is -n, which means whatever is after the -n is going to be a string, which is representing a base 10 scientific notation. Um, and if you don't give it the right number of parameters, or if you don't give it the proper format, it will report an error and just quit. All right, so that's enough talking. It is time to run the program. When you're ready to run the program, the first thing you need to do is to select the programming language, which in this case is just plain C. It's not even C++, okay? This is just plain C. And then you click debug. If you're new to debugging a program, then it will be helpful to get to know the usage of the debugger. You can go through this guide on how to use debugger. Well, guess what? I already know how to use GDB, so I don't need to go through that. If you're new to GDB, you might want to go through that. All right, so this part is really important, is when you run the program from inside GDB, you have to give it the option of run and then -n, and then you have to give it a number to process. So I'm just going to choose 1.23e negative 45, which is the notation to represent 1.25 times 10 to the power of negative 45. Is that okay? Because that's what we talked about, on last Tuesday and also the class before. Okay, scientific notation. So when you run this program, it will just kind of come back and that's it. There's nothing done. Okay. So if you want to figure out, okay, so what are we supposed to do here? Well, the first thing you want to do is to put a breakpoint in this particular function. It is called E10, which stands for exponent of 10, to exp2, which is exponent of 2. And this is where you need to put your code in. Okay, so I'm going to put a breakpoint here. In GDB, there are several ways to put a breakpoint. You can use the command line here and say B and then the line number on which you want to put a breakpoint, which is line 126. For those of you who are basically saying, I'm refusing to learn how to use GDB regardless of what, you can always put a dot here. If you put your mouse cursor on the left-hand side of a line number and click it, that's how you can also insert a breakpoint. A breakpoint, does everybody understand what a breakpoint is, or should I explain that? Okay, so what a breakpoint is when you run the program, when it gets to that line, it will pause the execution of the program. and then we'll say, okay, we are now at this point. What do you want to do? You can do a whole bunch of stuff. I'll show you what I mean by that. Are there any questions about using online GDB at this point? Yep.
Can you say again what the R represents? I mean,
R is run.
Run.
R is run.
And then negative N is what you said?
That is the option. In other words, this program is supposed can be compiled to run independently from the command line in any environment. So when you do run it on the command line, you have to specify the dash n and then the string, so it knows what it is supposed to process. Okay. Um, all right, so at this point, I can run the program again because remember, it completed its execution last time. So now it is time to run the program again. So I'll do a run dash n 1.23e negative 45 again, but this time it's going to stop. So when the debugger has paused because of a breakpoint, you would know because it would highlight this line. And at the same time, in the text area, it would also say it has reached breakpoint 1, which is on line 126 of main.c, because I didn't bother to change the file name on online GDB. Are we good so far? Okay. All right. So now that we are at a breakpoint, there's a lot of stuff we can do. I believe you can move this point here, so you can actually expose more of the debugger if you want to, which I think is really helpful. So at this point, you can use other commands, such as print. Okay, so you can print, some expressions like 12 times 34. Okay, so you can print, just constants and whatnot. But in this case, it is more helpful to print what is pn, which is the only parameter of this function. Okay, can someone explain to me what is PN based on the source code on line 121? What is the type of parameter PN?
It is.
Oh, okay, you go ahead first.
Pointer to a flow.
Pointer to a.
It is a pointer to a structure, like a custom.
Yep.
Flow.
It is a pointer to a structure. Very good. So the way we look at this construct here. Oh, do you want to add to his answer? No, you're good. Okay. So PN is, so the way you read the C program is sometimes you have to read it backwards. So in this case, PN is a pointer, which is represented by the asterisk, of a structure of the type float 102 or 102. Okay? So you might be asking, but you didn't say anything about what is a structure float or struct float of 102 or 102. Well, we can get, you can deal with that later, right? So now we can say in the GDB, you can say print pn, and it's just going to give you the type of the pointer and the actual address, which you can barely see because of the contrast. But that's okay. It's no big deal because it is not of any importance to us. We don't really need to know where the structure is, but we do need to know what is in the structure. So now can someone tell me how I can look into the structure that is pointed to by PN?
Scroll up.
Hmm?
You scroll up to go see where you define the structure.
Yeah, that's one way to do it. Go ahead. Yep, you can dereference it. But I think you guys are answering the question in a slightly different way. So you are trying to look at it from the definition perspective of what is a struct um, float 102, and there we have it. So a struct float 102 separates into a signed and unsigned 64-bit coefficient, a 16-bit signed E10 or the exponent of 10, and they also signed and also a signed 16-bit for exponent of 2. I think those things should ring a bell from our lecture on last Tuesday. Okay, so if you're working on this, okay, and these things are not ringing a bell, you might want to watch portions of the lectures, previous lectures. And while watching the lectures, take notes because it is going to be important. Okay, so now that we know what a struct float 102 looks like, it has four components. The sign really just needs to be either 0 or 1. Okay, the coefficient is 64-bit wide, and so instead of using 32-bit, which was how I demonstrated the procedure in class last Tuesday, now you have to deal with 64 bits. But the approach is the same. Okay, even though the width is different, it's doubled, the way you approach it is going to be the same. Okay. E10 is the exponent of 10. I think I use exp10 in the spreadsheet. And then E2 is the exponent of 2, which is exp2 when I talked about it using the spreadsheet. Is that okay? Because I do want to make sure everybody can make a connection between to the concepts that we have talked about last Tuesday. We good? All right. Let me put on do not disturb. In previous versions of, or in my previous phone, the do not disturb can be associated with my calendar. So whenever I have a calendar event, it will automatically turn off all the notifications. For some reason, Samsung doesn't have that, doesn't have the option to tie in my calendar with do not disturb. Okay, so anyway, so right here, so now we can now take a look at what is inside float. And someone may be saying, but that means I have to remember all of these different things in a float 102. Nope, not really. The debugger makes everything kind of easy. So let me go back to line 121, which is where the breakpoint is. And now we can say print, and exactly what you said. Using the asterisk symbol, we can now dereference the pointer. So now we can see that it has four components. Let me see, is it four? Yep, it has four components. The sign is a 0 because the number that I entered is non-negative. The coefficient is 123, not 1.23, because we only use integers to represent everything. Okay? The exponent of 10 is not negative 45 because when I multiply the coefficient, which was 1.23, so that it becomes 123, that means I have to somehow divide the whole thing by 100 somewhere else. And by decreasing the exponent of 10 by 2, I accomplish exactly the same thing. And then initially, E2 is a 0 because I have not, this is where you're supposed to show your code. So your code is going to gradually change the coefficient, E10 and also E2, so that eventually you'll be using all 64 bits of the coefficient. With the E10, that is 0. This is the annoying part is it times out because otherwise they have a process that's running, taking up resources. So you kind of have to make sure that you don't let it time out by. So now I have to run the whole thing again and say run dash n 1.23 e negative 45, and now we get to the same point. Oh, for those of you who absolutely refuse to use command line anything, you can also on the right hand side you can also see that you can use watch expressions. You can also examine stuff here. So that's your other option is to use the so-called graphical user interface. So anyway, let me get back to what PN is pointing to. So PN is pointing to a structure that has four components: the sign, the coefficient, E10 and E2, and we want to preserve the value of -1 to the power of sign times the coefficient times times 10 to the power of E10 times 2 to the power of E2. That value should be preserved as you work out, the final representation. Are we okay so far? Do you guys understand what the code is supposed to do in E10 to exponent 2? We have a general idea? Okay, all right. All right, so where did we, is there anything in the class that can help you with this particular homework assignment or project, however you want to call that? The answer is yeah, that's what we have been talking about for some time. So when you go back to, oh, this is like further down, with floating point number representation, that is the whole purpose of one entire section, which is section 5 of this module. So if you look at section 5, it talks about how to convert from base 10 to a double representation. You don't have to do the final steps of actually creating a double. We can leave the structure as the way it is described in here. In other words, you can just leave the representation to have a sign all by itself, a coefficient that is 64-bit wide all by itself. E10 should become 0 when you're done, and then E2 is whatever it needs to be in order for the same value to be represented. All right? So getting back to the notes, okay, because I do want to show you where in the notes, you can get information about this. Um, that's basically, the whole thing. Getting rid of the exponent of 10, this we have actually talked about already in class, but if you want to read this portion, you should be reading it also. And then section 5.2.1 is particularly related to this project because it says, what if the exponent of 10 was initially less than 0? So this describes what you need to do in order to accomplish, the conversion. And that's it. That's basically your next activity for this class. I'm not going to call this a lab activity because I don't think you want to get this done in an hour and a half. No? Okay. Nobody wants to say, but I really want to make this a lab activity so I don't have anything else to do after this lab is done in a 1 hour and 20 minutes. This would be a great programming contest kind of thing. But we'll get there in some other at some other time. So are we good so far? Yep. Go ahead.
When will this be due?
Hmm?
When will this be due?
I will make it due in a week. So you will have 1 week from today to work on this, and you have to turn in your code, and I'll test your code to see whether it works or not. And most of the time, I would actually read the source code too. And in certain semesters, I would actually recognize, hey, this program looks exactly the same as that program in terms of spacing, the naming of the variables, and so on. Go like, okay, suspicious. And some other years, I would get programs that do not even compile. Even though it looks like it has everything in it, but it doesn't compile because the person who entered the program put in some kind of minor syntax mistakes. So that's also a suspicious kind of thing. It's like, why would this program be almost entirely complete and working if it's not for those few syntactical errors? That is okay. I will tell you, this does not happen naturally. There's no way this is the result of actual code development. All right. Any questions? You guys know where to find the lecture from last Tuesday? Okay, because that might come in handy. You guys know where to find the spreadsheet? Remember that spreadsheet that I used to demonstrate the logic of how to do things? Okay, so that might come in handy as well. Okay. A few other things that can come in handy. Okay, let me give you those pointers. One is to look into stdint.h. So you can look up, the header file because somewhere in the header file is a macro that will give you the largest value that you can represent in a 64-bit unsigned integer. And yes, I did not say exactly what it is because I want you to find it. Is that okay? But I'm giving you a pointer. It's somewhere within the header file. There is a definition of the largest value that a unsigned 64-bit integer can represent. And that's going to be useful in your program because you need to find out when to stop the doubling. And the condition to specify when to stop the doubling will need to know, what is the largest value that you can represent as a 64-bit unsigned integer. All right, so I think that gives you all the resources that you need to kind of get started with this program. Um, I would start on it as soon as possible. Today's lab is not exactly the usual lab. You are more than welcome and encouraged to stay here to at least get started with this program. Um, but you don't have to. But to the class on Thursday, it's a good opportunity to ask questions. Okay, so try to get it started and try to understand as much as possible. And then if you have questions, you can ask those questions on Thursday. Are we good so far? So I can tell you the experience from past semesters. Um, in the past semesters, next Monday at around 10 p.m., I'll get like a flood of incoming emails because that's when people start to get started with it with the project because it's due the next day. Well, guess what? I go to bed at 10. But Tech, aren't you obligated to answer questions from students? Yes. Read the syllabus. I have a policy of I will reply within 24 hours. So if the question was asked at 10 p.m. on Monday, I have until Tuesday at 10 p.m. to answer the question. So the point is get started early, okay? Get started early so you have an opportunity to ask questions and I have enough time to respond to your questions. Are we okay so far? You got a week to do this. And unfortunately, to some people, it means I have 6 days to procrastinate. Sorry? Yes, that would be myself. Okay, so I got to tell you this. I'm not trying to. Um, okay, I'll just tell you the facts. Okay, this is actual factual. I took a class in compiler design in San Francisco State University, and usually the homework assignments are due in 2 weeks because those are far more complex than this. Okay, you have to write a lexical analyzer, a grammar analyzer, code generator, and stuff like that. So each project has about 2 weeks of time for people to complete the assignment. I'm usually done in the first 2 days. That has nothing to do with whether I'm smart or not. It only has to do with I really like the homework assignments. So I end up spending all the time in the lab, to work on the homework assignments. The TA ended up not working on his version of the code, so that so that he has a model to kind of check the other students' code. He would just look at me and go like, "Tech, are you done with yours?" "Yeah, I'm done." And then he would just use mine as the standard. So because getting started early does not mean it's using more time. Procrastinating usually end up taking more time and more resources than starting earlier. So that's the whole thing. I mean, if you start early, if you start today right after class during the lab time, you're not losing any time. You're just reallocating time. You're just determining, how to use your time. Are you going to use it up front or are you going to push all the way to the end? That is a choice. Okay? Yep.
And where did you store that beginning code?
The beginning code is in the assignment, which is not yet available to you. So I can make it available right now. I mean, there's no reason why not to, except, I know some of you will try to get started on it right away. And it might be distracting because I still have other things to talk about in today's lecture. All right, so let me get to. So it's not exactly a lab this time. It is more of a programming project in C and C. I mean, if you want to see as C++, that's fine too, but it's not exactly that. All right, so where is it? Negative exponent. There we go. All right, so I will make it available to you like right now. Um, but the idea is, try not to get distracted. Today is the 4th, so it's going to be the 11th, October 11th, and I'll make it due at 9 a.m. There we go. There's no access key to get into this one, so you guys can get in right away. All right. So there is that. So what we're going to talk about today is what do we do when the exponent of 10 is positive? Because last Tuesday we talked about what if it is negative. So what we'll do today is to talk about, okay, what if it is positive to begin with? I'm going to use the spreadsheet approach again. So let me go to Google Drive, okay, add a new tab, and navigate to the shared portion, which means as soon as I create the document, you'll be able to see it. So new spreadsheet. And I'm just going to call the document based on the number it's supposed to process, which in this case is negative 1.23 times 10 to the power of 45. All right, so you should be able to see it now. All right, so first thing first is how is this particular value of negative 1.23 times 10 to the power of 45, how is it represented? This is the input string, so how is it going to be represented by the program? Well, now that we have online GDB up and running, I can actually kind of cheat and let that figure out how it is supposed to be represented. So let me go back to online GDB, debug the program again. And this time I'm going to run it with R, dash n, and then specify negative 1.23 times 10 to the power of 45 instead of negative 45. Press the enter key. Now we get to the breakpoint, same thing. Print whatever Pn is pointing to. So this time we have sign being a 1 because the quantity is a negative quantity. We have the coefficient as 123 again. That's expected, okay? That's exactly what we think it would do. But E10 is not 45, it is 43, because remember, you have to decrease the exponent of 10 by 2 to compensate for the coefficient being multiplied by 100. Is that okay so far? How things are represented? Okay. So given this is the representation of the value, now I can go back to the spreadsheet. So I can now go back to the spreadsheet, and now I can say column A is going to be the coefficient, which is kind of like the mantissa, except it doesn't have that requirement of it needs to be normalized. And then column B is going to be E10, the exponent of 10. Column C is going to be E2, which is the exponent of 2. The sign is not represented here because it really doesn't play that much of an important part during the conversion. And then finally, we have V, which is the value being represented. So right now, the coefficient is 123, E10 is 43, and then E2 is a 0 because we're at the beginning of the entire process. The value being represented is always going to be the coefficient times 10 to the power of E10, which is this cell over here, times 2 to the power of whatever column C is representing in that particular row. So, we got our value back. Okay, that is good to know. Okay. Now, what do we do next? Now, this is with a positive exponent of 10. So that means we can now try to decrement the exponent of 10 by multiplying the coefficient by 10. That's one thing we can do. But I'm not going to do that, okay? I'm going to use the same approach as last time, which is to maximize the coefficient until the coefficient can no longer be doubled anymore. So we'll try doubling the coefficient as much as possible so that we end up with a really gigantic, huge value before we try to do something about E10. Actually, let me think. Does that make sense? Yep.
How will we then reduce the coefficient later? Do we just increase it? We just increase the E2 to reduce it?
So you have to, because we are supposed to be multiplying the coefficient by 10, So you have to leave enough room for the multiplication by 10. Yep. But at some point you won't have space to do it anymore. So I want to emulate here what happens when you don't have space to do it anymore. All right, so we have now another column to say, fit does the coefficient fit in 32 bits. So remember, in your code, it's going to be 64 bits, but for the example, I'm going to use 32 bits. So once again, that is simply a comparison of whether the coefficient is less than 2 to the power of 32, the whole thing. Yep, just less than that. And we're still good. All right, so now we are going to try to double the coefficient until we can no longer double that. Let me see. Okay, so we'll double this first. So this is going to be the previous cell times 2. This is going to be preserved. And this is also, oops. All right, one more time. This is going to be preserved. This one we have to change. So we have to subtract 1 from E2. So it's going to be the previous one minus 1. And this one is still exactly the same. And this is still exactly the same. Oh, that doesn't work. Why is it not working? Oh, because E10 is, okay. So this is supposed to be the same as that. There we go. All right. But this time, this is no longer just A3 being less than 2 to the power 32 because we have to leave enough room for a multiplication by 10, right? So that means we need, in one way, we need A3 times 10 to be less than 2 to the power of 32. So A2 times 10 has to be less than the power of 2 to the power of 32 because you have to multiply the coefficient by 10 in order to get rid of, in order to decrease E10 by 1. All right, so now we are just going to do the same thing as last time, which is kind of let go all the way down to about, I would say about here. All right, so we got a few falses. They're not needed anymore. So I just need the first false. All right, so at this point, we end up with an integer that if I multiply this by 10 one more time, it won't fit in a 32-bit unsigned integer anymore, which means it is time for me to multiply this by 10. All right, so let's do that. So now we take this particular value and multiply that by 10. And as a, go ahead. Questions? Nope. Okay. Yep, go ahead.
You said if you multiply it by 10, it will not fit in the 32-bit anymore, right?
It will still barely fit, I should say. If you multiply it by 10,
Oh, it's less than. Got you.
oh, but when it does exit the loop, it is no longer less than. You're right. Okay. Because if you look at the condition, it says, if A32 times 10 is less than 2 to the power of 32, so that means you still have room for one multiplication.
Wouldn't it be like the power of 2 to the power of 32 minus 1 since it's like
Well, if it's less than.
Oh.
If it's less than or equal to, then you need the minus 1 after the 2 to the power of 32. Okay, so the way it is set up is working because this number here does fit in 32 bits. Okay, let's double check. Okay, does this number fit in 32 bits? So let's see, 3, 3. Nope, it does not fit in 32 bits.
On the previous one, the 123.
Oh, because I should be using this one. when it is still true, not when it is false.
That's what I was thinking.
Okay, sorry. This is the last value that we can use, and then we can multiply this by 10. There we go. And as a result, this E10 is now the whatever it used to be minus 1, because if I multiply 1 by if I multiply the coefficient by 10, then the exponent of 10 has to decrement by 1. E2 is still going to be the same as this one here, which is the last one that we got. And then the value should not have changed. So if I copy this equation formula and put it here, we still get our 1.23 times 10 to the power 45 here. And then we also want to copy this over here and see if it still fits in 32 bits. And this one is false because we just made the adjustment. So now is the time to go like, okay, what do we do at this point? Because if we double that coefficient, it's not going to fit in 32 bits anymore, because it's this thing times 10 is no longer representable in 32 bits. So this time we need to make the coefficient smaller. So what mechanism do we have to make the coefficient smaller so that we have room to multiply by 10 again?
Division or subtraction.
Division, okay, division is good. What are we going to divide it by? Now you have to be careful, because if we divide it by 10, then we end up changing exponent of 10 and we have to bump it up again, which defeats the whole purpose.
2.
Division by 2, very good. So remember, in the previous program, we keep doubling, by doubling the value of coefficient. This time we are going to do the half thing. All right, so now we say, okay, let's make the coefficient about 1/2 of what it used to be. But we cannot use 1/2, because if you divide something by 2, you're going to lose something, right? 3 divided by 2 is what? In integer math is 1, but it really is 1.5, right? So you're rounding down, you're losing something. So that means the rounding thing is also important. Do you guys remember how we got around the rounding thing? By not using the round function?
Oh,
I think we added 5 and then divided by 10.
Yep. So this time we have the divided by 2. So what should I add to the numerator before the division? Exactly, 1/2 of the denominator. Okay, so we're going to use about the same trick. So this time we're using the floor of, what did I say? Oh, right. This value plus 1, the whole thing, divided by 2. Now, in this case, it does not make a difference because this number is an even number. So, you can just use straight up, division by 2. But if it is not, this will give you the rounding effect that we needed in order to preserve, in order for the, in order for the error not to bias. Because not doing the rounding, in other words, if you don't do the plus 1 over here, then every single time you do a division by 2, your error is going to be on one side only. It's always going to be less than what it's supposed to be. So the bias can add up, and then before long, the value that you're supposed to be representing is no longer acceptable anymore. It's not going to be within the margin of error that we want. So that's it. So in this case, E10 is going to be preserved, but E2 is the one that is changed. How should I change this E2? We know it is based on this one here, but because I just divided the coefficient by 2, what should I do to the exponent of 2 to compensate for that?
Add 1.
Add 1, increment. Okay, very good. Excuse me. So we just say add 1 to it. These two are going to be exactly the same. So this is telling me that we still do not have room for another multiplication by 10 to the coefficient. Is that okay? Because that's what it's testing. Okay, if you look at the formula, this false here is asking do we have room for another multiplication by 10? And the answer is no, we do not. So what are we going to do next? Go ahead.
Keep doing that.
Keep doing that. Very good. So you have to, when you listen to yourself, when you say keep doing it, that's telling you if you were to translate this into code, you're looking at a loop. Now, is it a do while loop or a while loop? Well, you have some flexibilities there, okay? But it is going to be a loop, okay? So that's important. All right, so I'm going to highlight this entire row and say, let's do this one more time. No, no cigar. And do it one more time. Aha! There we go. So now we have the room for another multiplication by 10. Is that okay? So we look at this number here and go like, yep, this is good, because now we can kind of repeat the columns, okay, but not exactly. But now we can say, okay, the coefficient can now be this one, because this is the one that has room for another multiplication by 10. So you say, okay, we can now multiply this by 10. And as a result, the new exponent of 10 is going to be decremented one less than what it used to be. So this is based on what this one, okay, this one technically is the same, but we'll use that one. We can now subtract 1 from it. So now we have an exponent of 10 of 41. The exponent of 2 is going to be exactly what it used to be, which is negative 18 here. And then V should be preserved. So these two I can just copy because they are not changing in terms of the way the formulae are set up. So now we have, we are starting another iteration. This is the starting point. And I'm going to go like, okay, let's divide. Whoops, no, 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 no. Let's do it one more time because I need to use this to copy to the other side. Copy, paste. There we go. All right, so we just divided 3.2 billion or so, by 2, and we still don't have enough space for another multiplication by 10. Let's do it one more time. Still not enough. Do it one more time. Now we got enough space. So you might be looking at this and go like, oh, we need 3 iterations, right? Because that's what it seems like. Every time you multiply the coefficient by 10, you need 3 division by 2 in order to make enough space for another multiplication by 10. But that is not the case. Because remember, 10 is between 8, which is 2 to the power of 3, and 16, which is 2 to the power of 4. Which means most of the time, 3 divisions by 2 is going to make enough room for a multiplication by 10, but occasionally you need 4 division by 2. Is that okay? So do not make this loop count the number of times, but instead actually check to see if the coefficient can be multiplied by 10 again and still make it fit within a 32-bit unsigned integer. Is that okay? Because the observation seems to support that, oh, we just need to do it 3 times. But no, sometimes it would take 4 times. Yep.
So it's 3 or 4 times for this one and the previous one.
Say that one more time.
It's 3 or 4 iterations for this
Yep.
version and the previous version
Yes,
as well.
because it has to do with how 10 is fitting between 8 and 16. So every time you multiply something by 10, you need to divide it by 2, 3, or 4 times to make up for the multiplication by 10. And the other way around is true as well. So every time you divide something by 10, you might need to multiply by 2, 3, or 4 times. Yeah. So it really has to do with the log of 10 is between the log of 8 and the log of 16. All right, so are we good so far? Do you guys want another iteration or this is okay? This is okay? Any questions about this spreadsheet? I mean, you guys all have access to it already. If you want to make your own copy and then just kind of mess around with it or to document it, you're more than welcome to do that. I have permissions turned on so that you can go to make a copy. So you can actually just make a copy of this. I think with this one, you can download it as an Excel file. It will still work because it's very simplistic. So that's another way for you to kind of get a local copy so you can mess around with it or comment and basically just explain how this works.
I think this assignment, it looks very intimidating, but if you like kind of break it down,
Yep.
It isn't too bad. You got the double function, which just checks if it's greater than or equal to the max amount that you can fit in that bit length,
Yep.
bit width,
Mm-hmm.
and then you'll just decrease the exponent of two.
Are you talking about
Uh,
this one or the current assignment?
I'm talking about this one.
Yeah. So this one has a lot of similarity to the one that you're doing this week, like the one that I just assigned today. It's just that everything is going in the opposite direction. So instead of um, division by 10, you have multiplication by 10. Instead of multiplication by 2, you have division by 2. It's just everything is going in the opposite direction. Because in this case, you want to decrease the exponent of 10 from some positive integer to 0. And then the other one is doing exactly the opposite. You start with a very negative exponent of 10. You want to increment it to 0. So they are very much related. It's just that your conditions are set up differently, and what you do in the loop would be kind of the opposite of each other.
Would we have to like make a general function? So if you get a negative exponent of 10
No,
or a positive one, do they both work, or is it just the negative?
you don't. You can add as many additional functions as you wish, because that might help structure the code, but you do not have to. Yep. So the requirement of the homework assignment. Let me get back to GDB online GDB. So the requirement of your homework assignment is you can use any code you want within this portion. But in addition, if you say I need a few helper functions to make the code more readable, hey, go for it. Not a problem. Is that okay? All right. So the next question is, how do you know this program works or not? There's no output. There's no C out there, no print apps, unless you have an error. So how do you test this program? So,
Put
yeah,
a C out. You can put it in C out.
you can put a C out, but I would make a suggestion. So I'll make a suggestion. So let's just say that the algorithm ends up doing this. Okay, it ends up saying the coefficient is 2000 and E10 is now 0. This is obviously wrong. Okay, if someone turns in this code as the homework assignment, I will make it a negative score. This is not just a 0. This is negative. So E2 is going to be, let's say, negative 45. Okay. All right. So let's just say that this is the result. Okay. This is your code, and you want to see if it works or not. So the way you check whether it works or not is to put the breakpoint right after that. Put it here. So let me run the program again. So you go to debug, and the other thing is you might want to keep using the same value to check. Okay, so this time I'm using negative 1.23 times 10 to the power of negative 45. Run the code. Now we get to the debug point. So at this point, Pn is changed. So if I say print, asterisk Pn, it is now saying the coefficient is 2000 because I just made it 2000. E10 is a 0. Hey, that is good because we want E10 to be 0. It's negative 45. For whatever strange reason, I decided that negative 45 is the answer. So at this point, how do you check? How do you know whether this answer is correct or not? Well, you can plug it into the spreadsheet, right? So you can basically just calculate and ask, is 2000 times 10 to the power of 0 times 2 to the power of negative 45, am I getting back 1.23 times 10 to the power of negative 45? If it's not even close, that means this code is not working. Does that make sense? I'm not sure whether you can use the power function, from the print command. I'll give it a try. So it will be, first I have to cast 2000 into a double. So Pn points to 2000 time, I think it's pow, not power in C and C++. It may not work. I'll give it a try. So we are looking at 10 to the power of E10 of the structure that Pn is pointing to, times power of 2 to the power of Pn points to E2. Nope, doesn't work because pow is not defined. Okay, let me just ask. Yep, no power in current context. Is it power or power in the library? Hmm? I think it's power. Yeah. Yeah, I did not. Well, first of all, I did not pound include the math.h header file, and it's not linked to the math library either. But as I said, you can plug in these values into a spreadsheet, right? So even though the GDB cannot do it, you just plug in all those values um, into the spreadsheet, like the one that we were working on. I'm just going to start a new sheet so I don't mess up the nice one. So just plug in here and ask, what? It's 2,000 times 10 to the power of 0 times 2 to the power of negative 45. Am I getting back um, the value that I started off with? Now remember, in the spreadsheet, you might need to change the number formatting so that it would use the scientific notation. No, that doesn't look like negative 1. That doesn't look like 1.23 times 10 to the power of negative 45. So that means this is not likely to be the right answer. Obviously, it is not, okay? Because I'm just trying to illustrate how you can check whether your answer is right or not.
Imagine if you just, off the top of your head,
No,
just
no,
accidentally
absolutely
put the
not.
answer.
Absolutely not. Because remember, coefficient is supposed to be using all 64 bits. So we are looking at a number that has 19 base 10 digits. I can barely remember like a 3-digit code. Every time I use my credit card and they ask me what is the CVC, I have to look at it again. Even though it's the same credit card for years, it's like, what was it again? The CVC? Are we good so far? So that's how you check, whether your answer is correct, because you want to be able to get back to the original value, and also to make sure that your coefficient is using all 64 bits. Oh, but how do we do that? How do we make sure that the coefficient is using all 64 bits? In other words, we do not have any leading zeros with the most significant bits. We want bit 63 to be a 1. How do we check that? There are a few ways to do it.
Do you check its sign?
um, you can cast it into an int and then check the sign, yes. But that's really not a very good way to do it. Just conceptually, it is not, but you can, yes.
Like a bitwise operator we can use?
Hmm?
Is there like a bitwise operator that we can
Yes, there are a few bitwise operators that we can use. So let me use this opportunity to introduce bitwise operators that many of you probably did not learn from CISP360 because they didn't teach it. So we'll go ahead and print 1. Okay, I'm not sure. Can you guys see the bottom of the screen from the back of the classroom? Are you guys okay? I can, let me see. Let me just kind of, oh, let me just resize this screen, I mean the window, so this way, I can pull that up so people in the back, would have an easier time looking at the bottom of the screen. So a little bit more. There we go. Uh, yeah, there. Okay. All right. So, what was I about to say? Right, debugger. So you can pull the debugger out, and I can actually pull it all the way up because I'm only demonstrating what is a bitwise operator. Okay. All right. So now we can go ahead and print 1 left shifted twice. Okay. So let's see what that means. So now you have to look at 1 as a binary number. Yes, that's a trick question. What is 1 as a binary number? You guys know the answer? 1. Very good. Okay. So the left shift operator is basically saying, I'm going to pad this number of zeros to the right-hand side of this bit pattern. Are we go okay? So one left shifted twice is basically just 100 in base 2. What is the value represented by 100 in base 2? Unsigned.
That is 8.
Close.
Sorry,
4.
4.
Yeah, it is 4. Okay, so if I press the enter key, it just says 4. Now, if you want to kind of check your binary stuff, you can always do a slash t just to make sure that it is indeed 100 in base 2. So how is that going to help me, right? So if I want what is the most significant bit of a 64-bit unsigned integer?
2 minus 1.
Sorry?
2 minus 1.
That's the value, but what is the position? What bit position are we talking about? The most significant bit, what is the position of the most significant bit of a 64-bit unsigned integer?
Leftmost? It's the leftmost position?
Leftmost, yes. Bit 63, yes. So bit 63 is the correct answer. So the question is, how do I use the bit shift operation so that we have just bit 63 being a 1? Now, if you have bit 63 being a 1, how many zeros are to the right-hand side of that 1? Exactly 63. Very good. Okay. So if you want bit 63 to be a 1 and everything else to be zeros, you can now use the shift operator and say, I can just do this. Now don't do 64, do 63. So now that should end up with a number, a binary number, that has a 1 all the way to the left-hand side with 63 zeros padding on the right-hand side. Okay? This works sometimes, and it doesn't work some other times. It doesn't work in this case because in GDB, when you use an integer constant, it is understood as 32-bit. And that's why it doesn't work, because if you shift 164 times, but you're only using a 32-bit unsigned integer, you're going to get all zeros, right? So what you need to do in the debugger, okay, if you want to do this inside the debugger, what you need to do is to cast the 1 first as a u in 64, 64 underscore t. Now it works. Is that okay? Does anyone want to count the number of zeros? There's an easy way to do that, if you use a VI or anything that has regular expression, because the pattern matching thing can specify, I want exactly this many things in this pattern, okay? But I'm not gonna spend the time to do that. Okay, so, wait. Uh, okay, that's actually, okay. All right, so now what do you do? I mean, if you look at this bit pattern and go like, great. Okay, for this portion, I don't need to use GDB. So I'm going to cheat and just use GDB all by itself on the command line because it's really the same thing. All right, so getting back to what we had earlier. We have this. Oh, this is going to be interesting because I did not pound include, so I don't think UN64 underscore T is understood. Nope, it's not. Fine, we'll use the unsigned long long. There we go. That's basically what it translates to. So anyway, if you don't want to count the number of zeros, and I cannot blame you because I don't want to count that either, what is the other way to count, what base am I going to use? So I can actually look at the bit equivalency, but without having this insane number of digits. What base is closely related to base 2, meaning the conversion is going to be a table lookup little thing, but yet it has fewer digits, so I can actually do the counting a lot easier. Base 16, very good. Okay, so base 16 is going to be helpful here. So that means, instead of using print slash t, I can now use print slash x for hexadecimal. And then we look at this and go like, okay, but how do we know whether there is a 1 for bit 63 and then the rest are all zeros? Well, first of all, you deal with the easy part first, right? Count the number of zeros. I mean, there's still a lot, but a lot less than last time, right? So we'll count this time. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we got 15 zeros in this case, which is accounting for 60 binary zeros already. So we got 4 bits left, right? Because remember, this is a 64-bit pattern. We only got 4 bits left. The 4 bit that is left over is represented by the 8. So now you have to think, how is 8 represented as a 4-bit pattern? It has none of 1, none of 2, none of 4, but 1 of 8, right? So what does it look like as a 4-bit pattern? 1, 0, 0, 0. Wait, but that means we have 3 additional zeros. So that means we end up with 63 zeros and 1 extra one all the way to the left-hand side. We got the right bit pattern. Is that okay? Okay, now that we know how to um, generate an unsigned integer with the bit pattern that we want, how do we check whether that particular bit is set or not in the answer that you guys give me? Right? That becomes the question. How do we do that? So I am going to say, okay, let's take a look at another integer, which is, oh, let's try 4 billion something. Okay, so we'll try, well, actually, we can try 2 billion something. So we can say 2800, 1, 2, 3, 1, 2, 3. Okay, that's 2.8 billion, which is more than 1/2 of 4 billion. Okay, so if you look at the binary representation of this, it should have the most significant bit, which is bit 63, being a 1. Does that make sense to you? Okay. So the question is, how do I combine what we learned earlier and then determine whether bit 60, oh, I have to cast it again. No, this will work in 32-bit. Remember, we are dealing with 64-bit. So I don't want to generate a 64-bit number by hand that is guaranteed to have bit 63 being a 1. I can because I know the number of digits that I need to do that. So I will have a 19-digit number, which means I have to count here, count 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So now we look at this and ask, oh, that's not quite enough, is it? I need 1 more 0. There we go. Okay. So now we look at this number, which is, um, I mean, you can tell right away. This is one quick way to do it, is to print out your coefficient, count the digits, and make sure the most significant hexadecimal digit is at least an 8. Let me say that one more time. Print the coefficient in hexadecimal. Okay? You end up with something like this. It should have 16 digits. If it has fewer than 16 digits, it's not meeting the requirement right away. So assuming that it does have 16 digits, then you look at the most significant digit. It should be 8, 9, A, B, C, D, E, or F. If it is a 1, 2, 3, 4, 5, 6, 7, then you have not met the requirement. Okay. Does that make sense? Do you guys understand what I just said? And do you understand why that works? Okay? So different ways to accomplish the same thing. All right? So I think you got all the pieces for the assignment that is coming up, that I just assigned. And you probably have enough to start on the next one also, the positive exponent, but I'm not going to release that one yet. Okay, that one will be released on Thursday. So right now you can just focus on the negative exponent logic. Are there any questions about the syntax of how to access a member of a structure that is pointed to by a pointer? No? Okay. Um, all right. So I think the whole floating point calculation thing is pretty much done. We are going to start on the next topic. Let's take row first. Let's go ahead and take row because we have, I think everybody who is coming to this class are in the class already. So I think this is probably a good time to take row. Today is the 4th of October. Can you believe it? This is week 7 already of the whole semester. Okay, let me go to questions and show you the answer. Overflow. Right. Overflow. And then I'll give it to you. To 10:20. I mean, that should be enough time. Save and publish. There we go. So as you guys are doing this, just entering overflow for this activity, I am going to kind of move on to the next topic. So at this point, we are pretty much done with how values are represented. We talked about base conversion. We talked about the signed representation. We talked about the floating point representation. So all of those are basically ways to represent values. So we are now almost ready to move on to the next major module. The previous module has to do with number value representation and how we work with numbers. How do we add two numbers? How do we subtract two numbers? How do we know whether one number is less than another number? Those are the things that that we talked about in the previous module. The new module that we are moving into, I mean, we can barely get some kind of like a roadmap into this module, is called von Neumann architecture and memory. So this module focuses more on the control part of a processor. The previous one is how do we represent values? How do we work with values? How do we add? How do we subtract? How do we compare? This one is more like, but how does a processor get things done? Okay, other than just the calculation. So it starts off with the D flip-flop and other basic memory devices, which is basically asking, how do we make transistors, how do we arrange a circuit of transistors so that it can quote unquote remember stuff? Because right now, the adder doesn't remember anything. The moment you change one of the input pins, it's going to change the output. There's no way to say, okay, but I need to write down and remember the previous result. It has no mechanism whatsoever to do that. So a D flip-flop is the easiest device, the simplest device that has what we would call the ability to remember something. And I can give you a diagram, okay, because we're going to get into the details anyway on Thursday. So now I'm just going to give you a diagram of what a D flip-flop looks like. So a D flip-flop looks like this. You got two input pins, two NAND gates, and then you have two output pins, like so, except there's a little bit of a crossing of the circuits. That is a NAND gate. I mean, that is a SR latch based on a NAND gate. And I claim that this is the smallest and the simplest memory device that you can make. This is a NAND gate, which means I can use two P and two N transistors to make it. The other one is kind of the same thing. So this entire thing is going to take 8 transistors, 4 P transistors and 4 N transistors arranged in a particular way. But I'm claiming that this is the simplest memory device that you can make out of transistors. It's called a SR latch. This is an SR latch. And of course, people will be asking, but what does that stand for? What is S standing for? And what is R standing for? The module will explain that. And it's a weird memory device because it doesn't work the same way that most people think a memory, device should work. But nonetheless, it is a memory device. So we're going to start with that. And then we're going to move on to more complex memory devices and different ways of saying, hey, I need you to remember something now. Okay, so we will talk about all of those mechanisms, but this is the basis. This is the core of all of those other components. So that's going to be D flip-flop and basic memory devices. And then from there, we will continue to talk about the other control mechanisms inside the processor. So we will get to um, other components that you can find in Logisim. So we have not been touching Logisim for a while. And then now we're going to get back to Logisim. And not only are we getting back to Logisim, we'll be using Logisim from this point on, until the end of the semester. We'll be running C programs in Logisim, but you will be the compiler. All right, so you'll be looking at C code and then change the C code or translate the C code into assembly language to a processor that runs in Logisim. The entire processor is contained inside Logisim. So you get to see everything that is going on inside the processor. So in order for that to happen, we have certain components inside the processor that you need to understand. RAM is one thing, ROM is one thing, multiplexer and demultiplexer are the two other things. They are relatively easy to understand, so you can actually go into Logisim right now, go to the reference library, look up these items, and read it for yourself, okay? But we won't need it for a while, so if you don't have time, don't do it until we are ready to take on these topics. And just to finish up the roadmap until the end of the semester, so after that, we will basically start to use TTP. TTP stands for Text Toy Processor, which is entirely running inside Logisim. And then we'll talk about assembly language programming, how to call, how to return from subroutines, how to work with C control structures, how to deal with pointers, and so on and so forth. So by the time we get to the end of the semester, we should be able to translate simple C code into assembly code and actually watch that run inside the simulated processor. Do you guys want to take a look at what it looks like, the processor? Okay. Let me see if I can do that because it's in a different account on the same computer. All right, so let me do this. I should write a script to do this. All right, so I should be able to do it now. Well, this is really annoying because when I change my Xauth, it turns off the other monitor. All right, so I'm going to show you next time. We are running out of time for today's class too. So anyway, I was attempting to give you a demonstration of what the processor looks like, but it's really for it will be until like week 8 or 9 that we actually need it. So, it's okay not to be able to demonstrate it today. All right. Any questions before we call this the end of the lecture? Because it's still being recorded, just the audio. Yep.
Maybe go over the floating point 2 lab.
Can I go over
Floating point 2 lab.
floating point lab? Oh, the two? Yes. Let me. Okay, I need it. I can't turn the monitor back on until I fix that.
I'm so sorry, sir. I didn't realize that we did roll.
Oh.
It's all right.
Uh, remove. Okay. Hmm. It's going to take me some time to. Can you spell out the question? Maybe that would be faster.
The first question is in one step of series 10.
You can describe it, or I still have access to um, the web page. Give me a second here to get there. And your question is about 1, 2, 3, or 4?
I want
Which one?
1, 2, 3, 4.
All of them? Okay, sure. I will do that. Yeah, so this part I'm just going to explain using the whiteboard. And that is floating point 2. All right, so question number 1 is asking if x equals to a certain value, how do we determine what power of 2 to multiply it so that it is just barely fitting into 2 to the power of 64 minus 1? Okay, so I'll set it up here. So we have,
Where is this?
hmm?
Where is this?
This is the previous lab on last Tuesday.
Oh, okay.
Yep. So we have x times 2 to the power of p plus 5, and we want that to be less than 2 to the power of 64 minus 1, right? Okay, that's question number 1. So I don't even need to tell you what x is. X is a given value, but we want to solve for p, right? So in this case, you can use algebra, and you can basically say 2 to the power of p, well, there's no plus here, is going to be less than 2 to the power of 64 minus 1, but that's a plus 5 here, but that's actually not super important. So the plus 5 becomes a minus 5 on here, and then you divide the whole thing by x, right? So how do you solve for p when you have this inequality? So p is the floor of the log 2 of this thing here. That's basically the general equation. Is that okay? All right, it's the second question. All right, so the second question is easy because the second question is giving you a value and it wants to know whether the round versus the floor makes a difference or not, right? So it is basically asking you about the round of x divided by 10 minus the floor of x divided by 10. And it's asking you, does it make a difference? What is the value? What is the difference between those? Do you want me to explain this one or not? Because ultimately it depends on whether you understand what is rounding. Sorry? I cannot hear you.
I don't know actually.
You do not know what?
How to do that.
What rounding is?
I know how to work around it. It's just that the highest value.
Okay, but remember in the question itself, it also spells out one way to do rounding. So the round of x is the floor of x plus 0.5. That was actually part of the question. So you can apply this. Do you know what is a floor?
Yeah.
Yeah. So basically the question is really asking that. Okay. So that's question number 2, and then we move on to question number 3. Question number 3 is asking what is the number of 2 to the power of p in a particular value? So that would be just x divided by 2 to the power of p, and then you round it. So you round it up or round it down based on, okay, fine. That's how you calculate it. So that's of question number 3. Question number 4 is the hardest because it would seem that we have 2 variables, but we don't. So for question number 4, you have a certain value, b is given to you. X has to be between 2 to the power of 53 minus 1 and 2 to the power of 52. That is the constraint for x, right? And we want to figure out 2 to the power of p, what p needs to be in order for b times 2 to the power of b times, okay, let me check the setup of the constraints. Okay, so we need v to be expressed as some x times 2 to the power of p. This is one constraint, and this is the other constraint. That's basically what the question is asking. So what you need to do is to plug in and say, what if x is the minimum? Solve for this p, and then plug in what if x is the maximum? Solve for that p2. You end up with 2 p values. There's one integer between the 2 p values, and that will be the answer. All right. So okay. All right. I think with that we are done with today's lecture. So you're more than welcome and encouraged to stay here to work on your programming assignment that is due in a week. But if you need to go, that's fine too.